to continue the Mujin story a little more, in 2019, we expanded to China, and after that to the US. And QuickBot is being sold by Mujin USA, and QuickBot is a ready-made solution for the warehouse. Just a single robot that you can roll into your warehouse, and it will depalletize boxes for you. You don't need to know what's coming in, what kind of boxes are coming in. You don't need to register the boxes in advance. And the robot can do this registration process for you even. So you can rent the robot. It's robotics as a service. It's like paying the robot a wage, so to speak. And we made QuickBot because there's still a lot of obstacles to integrate robotics into the warehouse. And not every user wants to automate the whole warehouse at once. So this is a much more approachable and modular product, and it will lower the barrier of entry for many users. Well, I define myself as a roboticist. I work on tough problems in robotics, and I make robots do useful stuff. Originally, I studied mechanical engineering, and that's in Germany and in France. But I realized that I don't want to work with machines as much as I want machines to work for me. So then I started working in the humanoid robotics group with Tami Masbour in Germany at KIT. And then I got my PhD in Japan, and I stayed in Japan as a researcher with Omron SinicX. And I joined Mujin in 2021. My interest has always really been in making robots do useful things, like all the things that I don't want to do. So for example, in my PhD, I tried to make robots do laundry, and I have been doing robotics competitions. That's been very fun, like the Amazon Robotics Challenge, where robots pick and place things, and the Airbus Shop Floor Challenge, where robots drill things, and then the World Robot Assembly Challenge, where we made robots assemble things. And now I'm making robots do big things at Mujin.
So I'm curious to ask you, why did you change from working what you have been doing in your PhD to work in automated warehouse, which is completely different problems?
Right, that's a good question. But first off, let me say that even though at this time Mujin is providing a lot of logistics applications like warehouse automation, the vision is much bigger. In the long run, at Mujin we want to provide a controller that you can use to solve robotics problems without needing to be a robotics expert. So why did I change? What I've encountered in my research is that lots of times we have to reinvent the wheel to make a project work. That's my feeling anyway. I've had this experience myself in my lab, and I've heard similar things from many different people. Lots of people have to work on problems where one would think, that's just engineering, or that's been solved already. But in reality, these problems haven't been solved well enough that someone could just plug a solution in without a lot of custom work. So people end up re-implementing the same things, or it takes a lot of work to put them all together, and it feels wasteful. And what we want to provide at Mujin is one platform that provides all the building blocks, all the tools that you need to solve problems with robots with certified safety, reliability, high performance. And it is high performance, and it's well tested, which you can see by the fact that it's been running in production for thousands of hours already.
So I'm curious, since you have been involved with academia and industry, what was different, maybe significantly different in solving problems? And can you tell me more about what did you find out with the difference between both of them?
Well, there's many answers you can give to that. But probably the biggest difference to me is that in research, you only need to show that your method works on a prototype. And a common pattern is that the champion data, so to speak, ends up in the paper, and the difficulties, or the dirty laundry as I like to call it, is left for future work, or it doesn't really come up. Whereas in the industry, that's just the first step. When you need to show that your solution really works, you have to take it so much further. You have to solve so many more problems than that. To give you an example, just picking and placing items, it seems like a simple task, right? But when you really optimize it, when you try to shave down the cycle times, when you optimize everything, you parallelize your motion planning, you find a lot of problems that you didn't even have to think about in a research setting. Like which sampling methods perform better in a given environment, or for a certain robot, or for a certain gripper. which parts of the search tree do you need to prune, at what stage. All of these details, they end up having a big effect. So what I found is that even though research and the industry, they are different, when you implement the real thing and you push it to the limit, then you find very challenging and difficult problems that you need to solve, and they are often ones that you wouldn't have anticipated in the lab even. And to me, these problems, the ones that you face when you really try to make a solution as good as you can get it, they're very valuable and engaging, and they're almost like research.
I'm curious to ask you about Mujin evolution. It's almost now 12 years old. What do you think is the most significant and crucial part for startup survival, especially in the early stages? Can you tell me about what is really significant to make the company go for a long run?
How to decide what to do in robotics? Let me give you some background. Mujin was founded 12 years ago in Japan. And back in that day, the standard procedure to solve robotics problems in the industry was to do something called teaching and playback. And teaching is to define specific robot joint positions, like configurations, and you use those positions to program the robot, to make a robot program. So your robot would go to this position and that position, would close the gripper to pick something up, for example, go back, open the gripper to place something somewhere. So these are all predefined motions, and they're all made by hand. It's very repetitive work, and it still takes a lot of skill and time. And a problem with that is, apart from the fact that it takes a lot of time, is that even when a skilled expert makes these motions by defining the waypoints, it's not an optimal motion in generally speaking. You could almost always make it a little bit smoother. You could make it go a little bit closer around the edges so you can do the very optimal, very quickest path, things like that. And for motions that repeat a lot, you do want them to be very efficient as you can make it, because tiny differences in efficiency, they multiply. So for a researcher, the obvious solution is, well, you use constrained motion planning and you get the optimal motion. That's the problem. But in the industry, this just wasn't ready for production. So that's the problem that we tackled. We used software written by one of our founders, by Rosen Yakov, who many of our viewers, listeners, might know from OpenRave or IKFast, open source. And we made our first product called PickWorker, which plans these optimal motions for bin picking tasks. This took years to develop, by the way. This is not trivial at all. And we're still improving it after a decade. And this very optimized bin picking logic, that's part of what we're going to put into the hands of developers soon. Now, you also asked, how do you take this kind of idea to a solution? And that's less of a robotics question than a business question. And my personal view would be that you have to find the right problem. You have to identify, can I solve something? Can I solve a technical issue? And is there a market that would want to pay for my solution?
Maybe a follow-up question here. How do you ensure the product you develop have a great market fit, like Mujin controller, QuickBot? Can you tell us more about the equation here to ensure the great market fit? Why I ask this question? Because sometimes I see like great technology, but it doesn't solve a real problem, frequent demanding problem. Can you tell me more about that?
Well, if you know how to do this well, then you will make great money, because what you're talking about is product market fit, and finding it is very difficult. You need to have instincts, you need to have the right planning. It's how to be an entrepreneur, essentially. Identifying what makes a good solution, what the market needs, and if people are ready to pay for it. So this isn't trivial. If you can supply all of that at the right time, not too early, not too late, you'll probably have success. Not guaranteed. It's tricky. You need some luck. There's no clear-cut solution. Someone put it this way once. I've heard this. It's like asking a chef how to make good food. It's just too much to put into words, and I'm not even sure I'm the right person to make all these calls. I wouldn't know how to do this. But you mentioned QuickBot, and I can talk about that. To continue the Mujin story a little more, in 2019, we expanded to China, and after that to the US. And QuickBot is being sold by Mujin USA, and QuickBot is a ready-made solution for the warehouse. Just a single robot that you can roll into your warehouse, and it will depalletize boxes for you. You don't need to know what's coming in, what kind of boxes are coming in. You don't need to register the boxes in advance. And the robot can do this registration process for you even. So you can rent the robot. It's robotics as a service. It's like paying the robot a wage, so to speak. And we made QuickBot because there's still a lot of obstacles to integrate robotics into the warehouse. And not every user wants to automate the whole warehouse at once. So this is a much more approachable and modular product, and it will lower the barrier of entry for many users.
Could you please tell me more about the Mujin controller accuracy in placement and picking, and also being hardware agnostic? Can you tell me more about that?
One of the things that is special about our controller is that we are independent of the robot hardware and independent of the camera hardware as well. So we provide a separate controller, a separate physical unit, and you can think of that as the brain of the robot. It can control different robots from different manufacturers, and it receives data from different camera systems. So for any application, we can choose the robot and the camera that are best suited for that particular job. And the way we make it work is, well, with different drivers for each robot and each camera system. So for cameras, we get the data, the 2D and the 3D data from the system, and we run our own detection algorithms. And for robots, we control each robot on the joint level. So we stream real-time joint data to the robot, and we often have privileged access, privileged drivers that we've negotiated with the robot maker. It depends on the accuracy that you're talking about. So there's accuracy in placement, how far away you are from a target position, and that's the bullseye thing that you mentioned. Accuracy versus precision. And it will depend on the robot hardware that you're using and the camera and your detection algorithm too, and you can calculate that. But really, robots are pretty accurate to the order of less than a millimeter, and cameras get better all the time, so I don't think that that's really the problem or the heart of the problem. To me, the real question is, how do you make a robot reliable? How do you make it reliably succeed? And in my opinion, the best approach for that is to use sensing as much as you reasonably can, and to make sure that during execution, your sensing data matches your expectations. It matches what you're expecting to receive. So this can get really complex really quickly, but here's a simple example. Suction cups. Using suction cups to lift objects is still one of the most useful gripping mechanisms in the industry, next to parallel grippers, like these chucking mechanisms. If you use a suction cup to pick up a thing, then you can measure the air pressure in your tubes very easily. And it's very convenient, very cheap. If you picked up the part without a problem, if it's lifted right, then the pressure in your tubes will be like a vacuum or close to. So when you notice after lifting it up that you don't have that vacuum, then you notice that something is going wrong. Maybe there's no seal, maybe the object fell off. This air pressure is a super useful signal to tell if something is going wrong and you need to recover. But you need to implement that. And here's another example. If you have a force sensor on the wrist of your robot arm, if you lift up the object and you sense that you don't have enough force on, or you don't sense enough force on your wrist, then what's going on? Did you drop the object? Maybe you actually sense too much force. Did you lift an object that's too heavy? Did you get one that's too light? Did you pick multiple? You have to identify what's going on and identify the box that you picked. There are a ton of cases like this, and you need to keep checking during execution what's happening, during the whole picking loop, during the whole robot execution. You need to think about at which points do you need to make which checks, when can you ignore certain signals, which sensors can fail, which need redundancy. Sometimes a sensor might not give you good data, in some configurations only or in some situations, so you may want to avoid the situation, or when you can't avoid it, you might want to disregard the sensor data at that time. So all of this, evaluating sensor data, this can get really complex, not only to understand, but also to program it. And the more sensors you add, obviously, it gets exponentially more complex. So all of this logic is part of what we deliver with the Mujin controller. So you don't have to reinvent this and re-implement this. There's so many edge cases like this. I want to give you one more example. So once we used a distance sensor to speed up the system. It's optional, but we rely on it. And some dust fell on that sensor, and then it was reporting wrong data. So we didn't want to stop the system just because there's some dust, but we couldn't go as fast as we wanted to. So we learned that, one, when that sensor is compromised, we need to have an alternative program path around that. We can't depend on the signal to be perfect forever. But the system shouldn't stop either. It will just have to run slower. And then we need to display something to the user to clean up the sensor. We need to have this very specific error message to say, clean up that sensor. We even have an alternative now where we can just blow the air or blow the dust off the sensor. But it was a real lesson. And all of these lessons, they are part of our product. There's so many edge cases like this, so many things that you would never expect unless you actually go to the trouble of implementing the thing. You can get double picks, triple picks. A worker might forget a piece of paper or something on the pallet, and then your robot or your detection system gets confused. The robot might think you picked up an object, but it's just that paper. Or you might pick up a thin object successfully, but it might be porous and the air might be picking up another object underneath it as well. There's boxes with flaps on them that can break, so there might be damaged ones that you can't lift just from the top. You need to support them from the side. There's so many like this. And once again, part of what we want to do with our product is to make applications like this, behaviors like this, much simpler to set up.
You mentioned interesting point about the redundancy and uncertainty. So I'm curious to ask you how you may ensure the Mujin controller here, or in general, being generic towards this uncertain situation, unexpected scenario. Can you tell me what is the aspect you have to consider when you design the software, or can you tell me more about what you should consider in that case?
I think it's really important to note one thing. In real applications, the reliability requirements are crazy. They are extreme. Often you need to get success rates of 99.999, it keeps going, %, and that's no exaggeration. So reliability is really important. I had a talk about this at IROS 2022 in Kyoto at a workshop about uncertainty and manipulation. And there are a lot of examples in that talk about how we handle uncertainty at Mujin. So it's probably best to link that talk instead of repeating everything here. And I also published a paper about uncertainty in assembly tasks specifically that might be interesting for anyone who wants to learn more about this question. But in general, the way to deal with uncertainty is to use all the sensors and modalities that you have available, especially suction force sensing if you have it, and anticipating all the possible errors. That's to me the most important thing. Nothing really teaches you like running robots in the real world though. So you just need to test and find this the long tail of edge cases. And we've been running production for over a decade now, so we have a lot of those.
I want to ask you about the sensor and actuator and robotics now. Where do you see the state of the sensor and actuator? Do you think there's enhancement should be done? Is it expensive? Can you tell me what could be still missing in both of them from your experience?
I have two perspectives on that. One is my own personal opinion on tactile sensing from my own research projects. And the other is, what do we need for industrial applications right now? And if I'm honest, in the applications, at least for logistics applications, with current technology, current sensing and robots, you can get pretty far. You can solve a lot of applications right now. It's just that it's complicated to put it all together. And that's part of what we're trying to solve with the Mujin technology. Looking at it from the research perspective, if we talk about interaction and manipulation, then yeah, if there were better performing tactile sensors, I think many doors will open up. I really wish tactile sensing was better, personally. At the moment in the industry, we can't really use high-resolution tactile sensors. And there's multiple reasons. One is they're not really durable enough. There's often drift. And the signal, this high-dimensional signal, is really difficult to use. If you compare that to the on-off signal of just a suction sensor or a light curtain, then you can imagine it's much easier to write a program with that.
I had a talk with the CEO of Octinion for Agriculture Robot, and he actually voiced his concern about how the tactile sensors are quite expensive and also maybe not reliable sometimes. And I will just share what he said in this clip.
Really essential in mechatronics that you pick your battles and you don't use technology you don't need. And as far as I'm concerned, soft robotics, and then especially the idea of creating some sort of feedback, some kind of haptic feedback in the gripper, it's not feasible in horticulture for a number of reasons. First of all, it's economically not feasible because the part where you interact with the prop is the part that you have to replace the most frequently because of diseases and all kinds of infections. So that needs to be the cheapest. Putting a lot of technology in there is not the brightest idea. But the question also is, why would you actually do that? Because the reasoning why people put it in is actually a false reasoning. And the idea is that a human has haptic feedback. We want to pick like a human, so we need haptic feedback. But that's actually not true. A human only has haptic feedback if he moves slow. The example we always give, if you put 3 cans on a table, and the first 2 are full, and the second and the last one is empty, you tell someone to pick them up really fast. The last one that's empty is going to fly up. It's going to be a lot higher than the full one. And that shows that we don't have haptic feedback at speed, only when it's slow. If a human picker picks at speeds of once every 3 seconds and faster, he doesn't have haptic feedback. So why would we put it in a robot? It creates a whole lot of complexity. It puts a lot of cost on both the gripper, but also the motors, the drives. It's a very important cost driver, and it's clearly not needed.
I find this quite relatable to what you're already saying here. So what does it take to make them maybe affordable and reliable from your experience?
Well, I don't make or research sensors, so take my opinion here with a grain of salt. But I feel like I know that one of the reasons why this is so difficult is because the scale is so small. If you compare our own fingertip sensors, our own tactile sensors, the fingertips, they are so intricate. And that's the level of resolution and performance that we expect of our tactile sensors that we make ourselves, right? So you want to imitate this level of detail and the fine structures in them, but then you also need the durability to withstand all of the industrial manipulation that you will have to do with it. So that's a difficult compromise to make. And sadly, our machines, they don't self-generate like our fingers do, sadly, yet. So yeah, that's difficult. And another reason that it's complex is the data is complex, like I mentioned earlier. Like the signals that we get from our skin, we have our brain and it's trained a lot to process all that, right? I actually published something in my PhD that's a little bit related. If you perform this rubbing motion with your fingers, then you can detect if you have 1 or 2 layers of paper or textile in between your fingers. And it's because you can sense the vibrations in your fingertips, and they differ depending on the tribological interactions between your fingers and the paper. The interfaces are different. Anyway, you can actually train a neural network to do the same. So to distinguish that if you make a robot do this. But that doesn't actually get you to a working robot or to the level of reliability that you need. It's far from the 99.99%. Very far even.
Can you tell me more about who are the target client or businesses here exactly?
The target audience for the Mujin controller is really anyone who wants to use a robot to do something useful. At the moment, you might buy a graphics card to run applications on it or to accelerate your applications. In the future, you should be able to buy the Mujin controller to run robot applications or to make your own robot applications. So it will be your robotics processing unit that you can use without having to know complicated things about robotics. And what are the real problems? Well, I find that currently making a robot solution is just too difficult. It takes too much. The difficulty curve, it just goes so far up and so steeply once you want to use more than just the robot. If you want to move just one single object from one location to another, and the locations never change, it's always the same, it's not that hard. But then the problem is usually way more complicated than that. Like, you want to detect where the objects are. So you add the camera and the detection system. And then you want to recover from errors, so you add the sensors. And then with every extra thing that you add, the difficulty just goes up and the amount of things that you need to do increases. So that's how you get this common pattern in academia that I've been seeing. A PhD student wants to implement something new on the robot. They spend a year or more just trying to make the robot work, implementing stuff. And then they manage to do their thing, but then the next student basically has to start from scratch. And it's really a pity. So with the Mujin controller, what we're trying to provide is useful building blocks that you can use to set up robots more quickly, more simply. So you don't need years of study, you don't need a robotics super team of developers, you can just solve your problem.
So I want to ask you, how many use cases does already Mujin have? And if you can, just share with us what could be the most challenging use cases you guys already encountered.
There's plenty of times when we had to extend the capabilities of our product, and usually the way we approach these problems is first simplify it with clever engineering, and then extend what the product can do. Extend our capabilities so we can handle something more, something new, these more complex tasks. We're actually in a very fortunate position where we can choose the kinds of projects that we want to take on and that will improve the product. So, for example, we had a project with Fast Retailing. That's the company behind GU and Uniqlo, two big fashion retailers. And they wanted to automate picking in their warehouses. But it's actually really complicated items. So these are flexible clothes. They deform. They're like, some of them are in bags, some are not in bags, some have cardboard packaging on half the item, so they have different patterns, they change all the time. And just picking those objects, how can you guarantee that you can pick a completely deformable object like that and that you can detect it? Which parts of the objects will deform when you pick it and move it? Which parts of it can you even predict? And which parts can you not model? How to work around all this was a real challenge. So in cases like this, like I said, it's a mix. In this case, we made a special gripper, multiple actually, to be able to pick the things. And then we extended our software to be able to handle these cases, to be able to handle deformable objects. So now we can apply that to future projects and future problems. But honestly, there are way too many examples to list here, and the controller can be used to solve almost any industrial robotics problem. And we have applied it to factory automation, to logistics, to lots of very specific use cases already. And most often, the core picking loop is enough. And extending it gives you a very useful behavior very quickly.
So what are the main challenges still remained in automated warehouse, and what should be the level of autonomy be there?
Right. Once again, just to be clear, with the Mujin controller, you can solve general robotics problems, so not just the warehouse. But one of our battlefields is the warehouse, and we really want to improve the state of automation in there because so many people suffer from bad work conditions there. It's tough work. It's tough on people. It's just a classic example of dull, dirty, dangerous, and the kind of labor we want to eliminate. No one should have to do this work in the world I envision. So if you ask, what is the main challenge there? What state of automation can be achieved? Then I would say you can practically automate all of the parts of the warehouse right now. There are fully automated warehouses already. So for example, there's one in China that's run by JD.com, and we supply the robots. It's just that fully automated warehouses, they aren't very common. But there are also many where the owners or the operators of the warehouse, they say, it's too complicated to insert robots into our workflow right now, or they might want to use robots for some products, but not all of them. And they might want to keep some humans around for the edge cases or the special cases. And it's important that those people, they have access to easy solutions and they can automate little by little. In the US, I think it's about 80% of warehouses that have no automation at all. And that's a big gap to fill.
So maybe I want to take your opinion about using a humanoid robot on automated warehouse. I think we saw that maybe in agility robotics as example, but when you think about the practicality of using humanoid robot compared to arm robot, for example, or UGV in automated warehouse, where do you see the future looks like? Should we really invest in humanoid robot, or we just stick to using arm robot, for example, or UGVs in automated warehouse?
Right, there's many things to say about that. And obviously, humanoid robots and the image of humanoid robots working in the same workspace, replacing people or helping people, it's sexy. It's attractive, you can immediately imagine it. But humanoid robots, they are very, very complex machines, and they're not necessary for many automation problems. You don't need that level of complexity. In fact, you can, for most problems, simplify it so much that you don't even need an industrial robot arm at all. Even that would be overkill. I'll grant there are good arguments for humanoid robots in many applications, especially in the household. They fit into the workspaces designed for us. They can use tools designed for us, and humans can predict their actions better, so sharing workspaces would be safer. But in our case, for Mujin, we don't want people to be in the same space. We want to automate the whole process completely, so why would a human need to be there? They're just in the way. The robot should be doing the work by itself. We want to be able to leave them alone. And there's another consideration when you think about shared workspaces. We've had, as Mujin, projects with cobots, collaborative robot arms, and we can make the workspace safe. It's possible. But customers actually want high speed, and they need it. It's the economic reality. To make the robot worth it, we need to run them at very high speeds. And robots can be a lot faster if they don't have to worry about a human coming right into their path the whole time. If we leave robots alone in the cell and we give them full control, then they can work much faster. And isn't that what we want? Robots working for us, full speed, all the time?
So maybe I want to ask you in maybe a hypothesis that if we use this robot in outdoor, if it needed, in that case, where would the changes should be done? Is it software or the hardware if we need to have automated warehouse in outdoor environment?
We haven't had a need, as far as I remember, to work under the free sky outside. And if we did, it's really not that big of an extra step to put up like a roof or to buy a waterproof robot. We've been thinking about environments that are more complex or more demanding than a factory floor, but we're focusing on the planning and the setup and developing behaviors. And being outside, at least right now, is often more a hardware problem than it is a software problem. And we want to provide the robot brain, and that works the same way if you're outside or inside.
So I think this question is quite important. We all have this argument. Which one is more challenging, especially in robotic development? Is it the hardware side or the software side, and why?
Well, it's both. Robotics at the core, to me, is an integration discipline. So it's just so wide-ranging. There's a big need for both the hardware and the software to work together, and they need to do it in a very tight loop. To make a real robotic system, you need a very broad range of skills. You need real challenges to be solved on both the hardware and the software side. But at the same time, when you look at everything that's required and the level of technology that we're at, I think the hardware is less of a problem right now than the software. Robotics, and this is our CTO's opinion too, by the way, is a software engineering problem. It's much easier to design and build the hardware right now than it is to write the software that can run an autonomous robot that does complex things. There's this famous experiment from decades ago, and it had a great video that you should look up. They made remotely controlled PR2 robots do all kinds of tasks, like clean up with a broom, pick up a beer from the fridge, open the fridge door, and really what it showed is that the hardware is capable and has been for a long time, but we are struggling to write the right programs. And so the problem is on all levels. And I think it's clear that the software is much more difficult. Robots are already much stronger, faster, quicker to react than we are, but the software isn't quite there yet, and that's why we're preparing the Mujin software development kit.
Maybe I want to ask you what makes you fulfilled so far since you have been working both in academia and industry. What makes you fulfilled?
Well, one thing that's for sure unique about Mujin is that although we're in Japan, you don't need Japanese to work here. And it's a lot of extremely talented people. You know, if you want to work here, apply. But you asked about research and industry. And I was in a research and in industrial research before in academic and industrial context. And like I mentioned earlier, one thing that I was struggling with is the feeling of reinventing the wheel. The feeling that it's hard to make real lasting progress and that you have to do so many things at once. You're spread thin. I was spending a lot of time on hardware integration problems that seemed like they should have been solved ages ago, and where I thought, I need to make this work now. I just need to solve this thing, other thing, but I don't have the time to solve this right, to do it right, so that it's solved once and for all. And I found that frustrating. So I also loved about working in research that you get to work on these new and complex problems, and you get to talk and discuss them with bright people. But I find that many of the pleasurable things actually exist in industrial R&D as well. It's just as exciting to discover a problem in a real application and investigate that really deeply and to solve it so that someone else can use your solution right away and to just solve it. Done. That's great. You know, at academic conferences, something that you hear sometimes is when a problem isn't hard enough or an approach already exists, is it's just engineering. But it's really more than that. When you really get into the details, into the nitty-gritty, when you try to solve the problem all the way, you find gaps in there that are just as complex as a research problem sometimes. And they actually are sometimes publishable research even. So it's true, industrial R&D is not academic. We don't look for unsolved problems and write solutions for them. But the kind of satisfaction that you can get and the complexity of the things that you can investigate, they can absolutely be similar. So what I would like to tell young people who maybe were like me, who might be interested in a research or an applied career, is that both are real options and they're both fulfilling. So don't discard the idea of working in the industry just yet. There are many exciting and hard things that need to be done outside of the lab as well. Real applications, real products, they're not just engineering. They're real difficult problems and they're waiting for you.
Yeah. First of all, I would like to say I'm so grateful that I visited Mujin while I was in Japan. It was really a wonderful experience to see everything in action. I want to ask you, while we work at Mujin, what are the moments of maybe excitement and satisfaction? If you can share any, for anyone who may be interested in the future to work at Mujin.
Well, at heart, I am both a researcher and a tinkerer. So I get satisfaction from both the understanding things side and the building part of things. And when something that I've put together works and it's doing the thing I wanted to do, then there's always this exciting moment, this fulfillment, and saying, yeah, we did it. It's really doing it. It's so cool. The robot is doing the thing. But there's also like a week later where you go, okay, next thing, we got to do it. Got to do something cooler. So there is the satisfaction of putting things together and making them work. And I think most engineers can relate to that. But there's also finding out and understanding how things work, and that in itself is very rewarding. So it's not only making things work, but also finding out how and why they work that are both very satisfying to me. In terms of topic, it's just a personal passion, but working on manipulation problems, because there's so much going on with your fingers and your perception of it and the physics and the friction. When you understand more about all that and you get more intuition to solve these kinds of problems, you get more troubleshooting skills, you can make better systems. I found that very satisfying. And I hope we can show off something related to this soon. And I guess finally, and like very generally, it's very fulfilling to do good work that lasts and that's useful and that gets us forward as a society. And I feel like I'm very fortunate to be doing a job where I believe that it does that.
Something in your mind every day as a robotics engineer, maybe if you can share it, something every day you think about.
Something that is on my mind or advice. Well, I was asked recently what I would tell someone if they wanted to be a roboticist, and maybe that's a good response here. So I think as cliche as that sounds, sometimes being really curious and trying to get to the bottom of things might be the most important skill, especially in robotics. Because if you only make a tutorial work and you're like, yeah, I made robot, then that's fun, but you're really just scratching the surface. And what gets you forward as a person, an engineer, in my opinion at least, is to go deeper and to dig and to figure out, okay, why did that work? What can I change about it? How else can I do this? What can I do with it? Could I do it differently? How far can I take this? Why did this thing work but not the other? And really understanding what happens inside is very worthwhile. It takes you very far and it teaches you a lot. So I would say dare to work on the hard stuff, even if you don't get to where you want it to be, if you don't figure it all out, you will learn a lot. And if you're lucky, you'll end up doing both science and engineering. What better than that?
Any final words like to say for people listening or for robotics community they should consider?
Well, there's the obvious. Mujin is hiring in Japan, in the US, in China, and you don't need Japanese to work with us in Tokyo, like I mentioned. And if you want to work on hard robotics problems with great people like me, then get on our website and apply. We're looking forward to you. Thank you so much.